Here's another question, folks. It's a work energy and power that involves momentum and conservation of mechanical energy. Now, in this question, guys, um, okay, this question starts here, but I'm not gonna dwell on this. It's easy. Let's look at this one. Now, it says ABC is a frictionless part on a track, which is ABC. That's frictionless. There's no friction here, guys. It says A is a point 1.2 meter above the ground. This is the height, which is point A. Block P, this block of 0.3 slides from point A with an initial speed of 2 meters per second and reaches point B as shown in the diagram. So point B here, guys, it has a velocity in the height. So that means the mechanical energy here, it consists of the kinetic energy and the gravitational potential energy, right? So as the point block P slides down, its velocity increases. So when it reaches point B, it will reach point B with a velocity, which is the final velocity that is greater than the initial. This is the initial velocity, right? And as block B slides down, its height decreases. So that means the kinetic energy, the gravitational potential energy decreases to 0 here. So the height here is 0 and the gravitational potential energy is 0. Here the velocity is what? Is a maximum velocity when it reaches there. Even the kinetic energy is what? Is maximum there. Now the question, it says define the conservative force. Conservative force, guys, here is the gravitational force. It's the force in which the work done on an object is independent to the part taken between 2 points. Guys, stick to the exam guideline. So the conservative force here is the gravitational force, which is the FG parallel and the FG. Right, 5.2, it says calculate the speed of block P at point B. So we want the speed of this object as it reaches this point. Guys, here at this track ABC, there's no non-conservative force here, so I'll say this is a closed system. So closed system, no external forces, no non-conservative force, and the work done by non-conservative force is 0. It's very important. So it says calculate the speed there. So there are so many ways we can do that. So we can use the mechanical energy or the work done by non-conservative force. I'm going to show you both. So I will use the conservation of mechanical energy. The mechanical energy at A is equivalent to the mechanical energy at B because it's conserved. So it's going to be mgh initial plus half mv initial square and mgh final plus half mv final square. So now we substitute. So what we can do, we can cancel the masses there. We can cancel the masses. Have we given the mass? Yes, we're given the mass. So it's 9.8. What is the height there at point A? It's 1.2, right? Plus half the mass we cancel. The velocity there, it's what? It's 2, right? It's 2 square. Very important to square, guys. And then height finally, this is height final, and then this is height initial. So the height final is 0 because there's no height there, so the gravitational potential energy will be 0 there. So it's half and the masses cancel. We want that velocity at point B square. So when you punch that in the calculator, guys, and you punch that in the calculator and you square, so you divide by half, you get 20. The answer, it's 27,52. It's a VF square at B, and then you put the square root. It's going to be 5,25 meter per second. Right? I hope that makes sense, guys. Let's use another way. the work done by non-conservative, EK plus change in EP. Guys, since there's no non-conservative force, I said the work done by non-conservative force is zero. There's no friction, no applied force, no tension. So we put zero there. So eventually, when the work done by non-conservative force is zero, so this equation becomes the same as the conservation of mechanical energy. So it's going to be like this. It's going to be like this. So as you can see, guys, this will be the same with what we have done above. So it's mgh final, mgh initial. So guys, eventually it's going to be the same. Everything that we're going to substitute is going to be the same here, right? So what we can do, we can cancel the mass here. It's half. The v final is the one that we want. The v initial, it's 2 square. And then minus g, it's 9.8. And then the height final is 0. Height initial is 1.2. So when you put this in the calculator, guys, the v final there, it's going to be 5.25, exactly the same as that. Okay, let's move to the next question, guys. The next question here, we're given this statement. It says block P collides with the stationary block Q. So they collide, these two. So this one, it reaches this point with the velocity of 5.25, which is the initial. And then the initial of Q is what? Is 0. So these are the velocity before collision, right? So they collide. So after colliding, they will move off together, right, to this point, right, and climb up there. Okay, let's read. After the collision, the two blocks slides through BC, right, and up the rough incline CD. The frictional force acting on the blocks as they move up, so there's a friction here. So one thing that we need to note now, this system now, it's what? It's open here, right? Open system, right? Because there's a friction present and the work done by non-conservative force is not equal to 0 because there's a non-conservative force present. So we're given the friction there, it's 0.5 newtons, and the blocks come to rest at a distance. So we're given this displacement there, and then when they get there, the final velocity is what? Is 0, right? They come to rest. It's very important. Now they say here, state the law of conservation of linear momentum. The total linear momentum in an isolated system remains constant, right? Remember, guys, this is an isolated system. All this path is an isolated system. So now, guys, since there's a collision here between those two, since there's a collision, that means there's a momentum, there's a change in momentum. Now they said calculate the speed of the combination of blocks P and Q immediately after collision. So as they collide here, guys, with their initial velocity, they moved off together, right? They move off together. So we wanted their velocity after collision. So 5.2.4. So guys, we're going to use the conservation of momentum. Momentum before equal to the momentum after. So the mass of P with initial velocity, mass of Q times by the initial velocity. As they move off together, guys, their masses are combined. So this is that they have one velocity and one mass is combined. It's P and Q. So the mass of P, it's 0.3. 0.3, yeah, and its initial velocity, guys, this can't be the initial velocity. The initial velocity now, it's 5.25 of P, 5.25, and the initial velocity of block, it was stationary block Q, so the momentum is 0. So it's 0.3 plus 0.4. The mass of Q is 0.4, and we wanted this velocity of P and Q. So if you do the math there, guys, the velocity that you're going to get when you divide there, the velocity that you're going to get is going to be 2,25 meter per second, right? This is the velocity that they have after collision when they move to here. So they will collide and then they move up until point C. So the velocity that they're going to reach this point, it's going to be 2,25 meters. So this velocity is 2,25 is the velocity after collision, but at this point, at this track, it's going to be the initial velocity, and the final, it's going to be that, right? So let's go to the next question. It says calculate the height h reached by the combination of the blocks. So these blocks, they combined, they reach here, they started this track or this incline with this velocity. As they moved up, there are forces that are acting there. There's a frictional force going down, there's an FG parallel going down. There are two forces acting on it: frictional force, FG parallel, right? And the velocity decreases and reach that point at 0 there. So now 5.2.5, what is needed is the height. So to do that, guys, remember this is an open system. So in an open system, you can't use the conservation of mechanical energy. So before we use anything else, guys, I'll use the work energy theorem. Work done, the net work done is equal to change in EK. I'll show you the other way that you can do it. So the forces that are acting there, guys, it's the friction. So we'll do the work done by friction, work done by FG parallel is equal to change in EK. So friction is equal to change in X cos theta, and the gravitational force, very important, guys. If you look here, we have no angle, we have no height, and we're given the displacement only, so we can't use the FG parallel. So now we can substitute here. Remember, guys, the work done by a gravitational force, which is FG parallel, is equal to FG, or equal to the negative change in gravitational potential energy. So here we can just substitute here by what? By negative change in gravitational potential energy equal to change in EK, right? So clearly this simply means that, so we have that change in X cos theta minus, so this is going to be minus mgh final minus mgh initial equal to half mv final squared minus mv initial squared, and then we substitute the frictional force we were given. It was 0.5. It's 0.5, and the displacement, it was 0.3 cos 180 degrees minus the mass. Remember, guys, they move off together. The mass, it's 0.4 plus 0.3, that makes 0.7, 9.8. The height final is the one that we want. The initial is 0, so this is the height initial and this is the height final, right? So the height final is the one that we want. The height initial is 0, and then the mass, half mass, is 0.7, and combine. The final velocity is 0. They said it's going to stop at the top, so the initial is, it's 2.25. 2.25 square. Very important to square that. You're not squaring with the negative there, guys. You're squaring the only 2.25 there. So this is this. So the answer here, it's negative 0.15, the answer here, and the answer here, it's 6.86 h. There's an unknown h there, and the answer for this side, it's negative 1.77 1875. Guys, it's not good to round off while you're not done with an answer. So when you do your math there, your h final there, it's going to be 0.24 meters. Let me show you the other way, guys. The other way to do this. So what you can do, which is similar to what I've done, but in another way. So you can say the conservation of mechanical energy at what is the point? It's C and D. The conservation of mechanical energy C is equal to the conservation the mechanical energy at C is equal to the mechanical energy at D minus the work done by friction. Because if it was a closed system, guys, it was only going to be this. But now there's a friction, you minus the friction. But you can add the friction this side, but not having that. But it's like this one. When you minus, it means that the energy has been lost through friction. So it's going to be mgh initial plus half mv initial square equal to mgh final plus half mv f squared minus the frictional force, work done by frictional force, which is fk change in x cos theta, right? Which is, guys, if you look at this, is equal to this, is the same. Do you see? But this is a change, this is a change, and when this and this I change, this and this I change, and there's a work done by friction. Here's the work done by friction, is the same. Okay, now let's substitute. When we substitute the mass, it's 0.7 in combination, 9.8 height initial. It started at the bottom, so it's going to be 0. And then the initial velocity, and the mass is 0.7, and the initial velocity is 2.25 square, equal the mass is 0.7 times 9.8, and then the height final is the one that we want. Okay, let me move this to this side. We move it this side, and then we're going to have plus the mass at 0.7, should have cancelled the mass, and the final velocity is 0, minus the friction 0.5, and the displacement is 0.3, and cos what? 180. So if you do the math here, guys, it's going to be the height final, it's going to be the 0.25. so the height final is this. It's 0.25. It reached the 0.25. Thank you so much, guys. I hope you understood.